Last time we were talking about the interaction of two systems using the canonical distribution. I want to look at it from a slightly different angle. Let's look at these two systems separately. So let's talk about system A, calculating the probability of it being in state R with energy E sub R. System A prime, calculating the probability that it is in state S, S prime with energy E sub S prime. So if we were to calculate the probabilities individually, this is what we would get. Now let's put them in thermal contact and let them interact only briefly with one another. So the probability of both of these things occurring, where system A is in state R and system A prime is in state S, that's going to be equal to the product of the two probabilities, no surprise, which I can write as e to the minus beta times E sub R plus E sub S prime divided by the sum over R in S, e to the minus beta E sub R plus E sub S prime. So, as this is true, as long as the two temperatures are equal, beta is equal to beta prime. If they're not equal, then we can't use the canonical distribution. But what's going to happen is the systems will evolve until they do reach an equilibrium situation. They're going to redistribute themselves however they have to, such that eventually beta will equal beta prime. So this is very nice. And along with that, notice how much easier it is to calculate entropies of systems like this. The beauty in this is that when I'm doing entropies in terms of partition function, the partition function is basically an unrestricted sum. And that makes it much easier to count than counting numbers of accessible states in between two energy limits. What I'd like to do now is I want to come up with yet another very effective expression for entropy. Let's start with this though. Let's express our physical quantities of interest in terms of the canonical distribution. So e to the minus beta e sub R divided by sum over R e to the minus beta e sub R, which tells me I can write e sub R as e to the minus beta e sub R over Z. And I can also write my mean energy in terms of a probability like that. So in a general quasi-static process, E would change because the probability might change and also the energy might change. So I'm going to write some general change in the energy, sum over R, E sub R, dP sub R, plus P sub R, d E sub R. I guess there's two ways the mean energy can change. The work done in this process, I could write as dW is equal to sum over R, P of R minus dV of R, or I could write that as minus P sub R dV sub R. Now, doing any work, the energy of each state is changed by some dE sub R. The heat absorbed in this process, then I could write as dQ is equal to dE plus dW, or I could write dQ then is equal to E sub R dP sub R. Furthermore, I can write my entropy, knowing the heat, I can write this in terms of S is equal to K log Z plus beta times my mean energy, which I can write as sum over R, P sub R, E sub R. And this is K log z minus sum over r p sub r log z times p sub r from before. Right, this is k log z minus log z times sum over r p sub r minus sum over r p sub r log p sub r. Put all my terms together, what do I get? I get is equal to k sum over r p sub r log p sub r. So another way of writing entropy, very simple, is, I'm sorry, minus sign, minus k p sub r log p sub r. Very nice expression for the entropy. What I'd like to do now be another couple of examples using the canonical distribution. And let's start with the thermal excitation of atoms. So let's look at hydrogen atoms in the photosphere of the sun. Okay? So hydrogen atoms in the sun's photosphere. Temperature in the sun's photosphere is 5,800 kelvins. We ask ourselves, what's the probability, or the ratio of the probability, that an atom in the photosphere will be in one of the first excited states of hydrogen to the probability that the atom is in the ground state? And you may get a surprising result here. And the way we do that is, let's take the ratio of the probability that it's in the excited state S2 to the ratio that it's in the ground state. Probability for the ground state S1, and I can write that as just the ratio of the Boltzmann factors, e to the minus E2 over KT divided by e to the minus E1 over K. So very simply, I can find this just by taking the ratio of Boltzmann factors. I can write this as e to the minus energy of the excited state minus energy of the ground state times KT. Turns out that E2 minus E1 for in electron volts is just 10.2 electron volts. KT in electron volts is 0.5 electron volts. So the ratio of the probabilities then is going to be equal to e to the minus 20.4 or 1.4 times 10 to the minus 9. What that tells you is that for every billion atoms in the ground state, 1.4 of them are in one of the first excited states. Since there are 4 first excited states, that means for every billion, you're going to have about 5.6 atoms that are in the excited state. This is kind of interesting, isn't it? So for modern physics, you might recall that atoms absorb sunlight as they travel toward Earth. But only certain wavelengths induce transitions into higher energy states. So atoms tend to transition downward from higher energy states or excited states down to the ground state, or if they transition from a higher energy state to the first excited state, they'll emit what we call visible wavelength photons, or those Balmer lines that you studied about in modern physics. So if an atom in an excited state can transition that way, you'll see absorption taking place, and there will be missing wavelengths from the solar spectrum. And when that happens, that enables us to determine that not only wavelengths from hydrogen are missing, but we can also detect the presence in the sun of elements like iron and magnesium, sodium, calcium, and so on. So this is one of the ways that we learn what elements comprise the sun. Of course, it's by many times over. It's mostly hydrogen and then helium. And you have trace elements, trace amounts of the other elements. So that's one very simple example of how to use the canonical ensemble, Boltzmann factor. I'd like to redo or re-examine the ideal gas again because there are a couple of quantities that I'd like to get from this development that we're going to use later on. I want to do the partition function for the ideal gas. If I have suppose I have n non-interacting molecules in this ideal gas, I can write my partition function as the partition function for one of those elements divided by n factorial. So if I want to get Z1, I have to add up all the Boltzmann factors for all the possible microstates of a single molecule, where I can write e to the minus e of s over kt is equal to e to the minus e s over kt. And I'm going to call it e sub tr, s over kt, times e to the minus e int of s over kt. What this represents is the energy of translation of that particular molecule, and this is the energy of interaction of that particular molecule. So, for example, this might entail things like vibrational energy, I should say not interaction, but internal energy, which would be vibrational energy of the molecule or rotational energy of the molecule, again, relating to state S. So I can write my Z translation as the sum over translational states e to the minus etr over kt. I can write my internal Z as the sum over internal states e to the minus e internal over kt. Now, let's ignore this for now. We're just going to ignore the internal degrees of rotation. Let's add up the Boltzmann factors by counting all position and momentum states. We did this before. We're going to use a slightly different methodology than we used before. So let's start with a molecule confined to a one-dimensional box. So we're going to treat this, in a sense, quantum mechanically. You'll see why. So we've got a molecule in a one-dimensional box. The boundary conditions are it's confined to the box. Let's say the box has a length L. And so the allowed wavelengths, back when you solve the particle in the box, remember, lambda sub n would be equal to 2L over n, where n can be 1, 2, 3, all the way up. N would essentially be the number of bumps. By the same token, the momentum would be equal to h over lambda sub n, the Bogey expression. I can write as nh over 2L. The energy would be equal to p sub n squared over 2m, or n squared h squared over 8 ml squared. You remember that from the particle in the box. So for a one-dimensional partition function, I could get sum over n e to the minus b sub n over kt, which I would write as sum over n e to the minus h squared n squared over 8 ml squared times kt. Let's assume that neither the length nor the temperature are very small. Then we can convert my sum to an integral. And I can write my one-dimensional partition function as integral from 0 to infinity e to the minus h squared n squared over 8 m l squared dn. That would give me a square root of pi over 2 times the square root of 8 ml squared kt over h squared. Or simplify it a little bit, square root of 2 pi mh divided by h squared. mkt divided by h squared all times out. I'm going to define this as L divided by little l sub q, and I'm going to call little l sub q my quantum length. And of course, my quantum length is just going to be h over square root 2 pi m kt. Okay. So we'll go by quantum length. It's essentially the de Broglie wavelength of a particle of mass m whose kinetic energy is kt. So for example, the quantum length for nitrogen molecule is 1.9 times 10 to the minus 11 meters, which means that L over LQ is very large, which means that there are a lot of accessible states for this molecule. I can make the same argument in 3 dimensions. So rather than using a 1-dimensional box, I could go to a 3-dimensional box. And if that's the case, I'm summing over nx, ny, and nz. And following the same argument, I'm going to get that for 3 dimensions. I'll get e to the minus e translation divided by kt, which is just going to give me a sum over nx, sum over ny, a sum over nz. And I'm going to get a factor of e to the minus h squared and x squared over 8mlx kt, lx squared kt, and then the same thing for ny and the same thing for nz. Do the same process as before, and I'm going to get an lx over L quantum, an Ly over an L quantum, an Lz over an L quantum, just the way we did before, which I can call V over V quantum, where now V quantum is the quantum volume. And that's going to be equal to, as we would expect before, my quantum volume would be equal to h over square root of 2 pi m kt. But in this case, all to the 3rd power. We call the quantum volume. So in this case, the translational partition function is essentially the number of de Broglie wavelength cubes that can fit in the volume of the box. That being the case, let's say the following. I can write for the single particle, Z1 is equal to V over VQ times Z internal. For the entire gas, then, I should be able to write Z as 1 over n factorial V Z internal over VQ to the nth power. By the way, the n factorial, the 1 over n factorial, we haven't talked about that very much, is necessary because these particles are indistinguishable. You can't tell one of them from another. And we'll talk about that and the problems that arise in that as we go deeper into the course. But be that as it may, we need that n factorial in there. I want to take log z, because log z seems to give me everything I'm looking for. I get log v plus log z internal minus log n minus log my quantum volume plus 1. From here on, we get everything else that we want. I can get an energy is equal to minus 1 over z dz d beta. And that's going to give me minus d log z d beta. I work all that through. I'm going to get essentially, I'll get minus n dd beta log z internal plus n over dq dvq beta, which is going to be n times E internal mean plus 3n over 2 beta, which is U, I should say E internal plus 3/2 n kt. So I want some other quantities from that. Suppose I want the heat capacity. Heat capacity is going to be dE dt at constant volume. I can write that as du internal dt plus 3nk over 2, a not unfamiliar result. My Helmholtz free energy I can write as minus kt log z, which will give me minus n kt log v minus log n plus 1 plus f internal. My pressure I can write as df dv at constant t and n. That's going to give me nkt over v, which you recognize is the ideal gas law, as we would expect. My entropy minus df dt at constant v and n. That's going to give me nk times the log of v over n dq plus 5/2. This minus df internal dt. And finally, my chemical potential I can write as df dn at constant t and v, and that's going to be minus kt log of v z internal divided by n times the quantum volume. So these are all kinds of thermodynamic quantities we can get using the partition function. We will have many, many more applications of this next time.